All right, welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute and ask. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences, and therefore no classified discussion is allowed. So please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now let me introduce our speaker today. It is an honor to host Ben Erichson, who is an assistant professor for data-driven modeling and artificial intelligence in the Department of Mechanical Engineering and Material Science at the University of Pittsburgh. Before joining University of Pittsburgh, he was a postdoctoral researcher in the Department of Statistics at UC Berkeley, where he worked with Michael Mahoney. He was also a postdoc at the Department of Applied Mathematics at the University of Washington, working with Nathan Kutz and Stephen Brunton. He earned his PhD in statistics at the University of St. Andrews. Ben's work is broadly interested at the intersection of deep learning, dynamical systems, and robustness. He is also interested in leveraging tools from randomized numerical linear algebra to build modern algorithms for data-intensive applications, such as fluid flows and climate science. Today, Ben will talk about continuous networks for sequential predictions, which is a very interesting topic. So please enjoy and expect a wonderful talk. Now, without further ado, let me pass the baton to Ben by asking one random question as usual. Today's random question is, I guess it's not random, it's these days the same question. Okay, what is your favorite things to do other than research?
Oh, okay. I think I'm a passionate skier. I do ski racing, so yeah.
Wonderful. Is there a ski area in near the school?
Well, there is. I actually been out this winter in Sun Valley, Idaho, because I didn't have to teach. But there's some smaller ski resorts down here. It's called Seven Springs.
I see.
Which is about an hour south of Pittsburgh.
Wow, I'm the beginner of the ski in the ski. I guess I better learn from you. Ben. All right, the stage is yours.
Okay, perfect. Thank you so much for the introduction. Very glad to be here and to talk a bit about my recent research on continuous networks for sequential predictions. And that's joint work with Liam, Alejandro, Sonhu, and Omri, and Michael Mahoney. So let me start with giving you a little bit a game plan for today's talk. So I start with a brief introduction, and then I kind of briefly talk about ODE nets, so just that we have all the same pickup point, and then switch to kind of the discussion of continuous time recurrent neural networks. In particular, I will discuss three different formulations, like Lipschitz recurrent neural networks, and then noisy RNNs, and our latest work, LEMS, long expressive memory. I will not probably get to dynamic autoencoders since I just have roughly an hour. So the main talk will be focused or centered around recurrent neural networks. I assume you're all very aware of what sequence modeling involves, right? Where we try to map an input sequence to a target sequence. But there are many different variations to this problem. So it's the simplest case. We just want to have a single input, which we map to a single target. And then we have the other situation where we try to map a sequence to a single target, or just a single input to a sequence. Or like I think the most challenging problem set up is that we want to map a sequence to a sequence. And in general, these problems can become very challenging if we deal with like data from some dynamical systems which feature rich multiscale and nonlinear temporal structure. examples might be turbulent flows or some climate data. But we have also this prediction if we have basically tried to analyze video streams which are recorded by a self-driving car. There are many classical models for sequential predictions. The simplest one are probably linear models or exponential smoothing or Riemann. These problems are very robust, actually. And by robust, I mean they have low variations. They don't give you a crazy prediction. Oh, sorry for that. But the main challenge is that these problems do not really scale to high-dimensional data. So assume like you try to model a fluid flow, which has maybe which is typically very high-dimensional, or some climate data. And they also obviously struggle with modeling very complex nonlinear dynamics. So neural networks are known for being able to handle very high-dimensional data. So there's no surprise that there are many neural network-based techniques for sequential predictions. And one of the classic framework architectures for this task are recurrent neural networks, and its many variants like gated recurrent neural networks, LSTMs, and so on. More recently, there's a lot of interest in transformers, which have like basically shown great success for natural language processing, but they are also now used in all kinds of related domains. And there are also very interesting other techniques like causal temporal convolutional networks. But in this talk, again, I will mainly talk about recurrent neural networks. So one of the main issues of these, I don't want to say traditional neural network techniques is that they're quite often a little bit brittle and prone to fail. So they're not very robust. They give you very good point predictions, but they can also fail dramatically. And that's an issue if these models are used in mission-critical applications such as self-driving cars.
Hey, Ben, I'm sorry to interrupt, but you know, on the title area, there's just some, you know, what is the Firefox symbol and the video symbol? Can you move that away if possible?
I don't. Oops. Okay.
Is it possible to move that? If not, don't worry about it. I mean, it's just covering some of.
Yeah, I don't know what do you see now?
I see the slide screen.
I'm not sure. Oh yeah, I see. That's an issue.
If you can move, that'll be wonderful. But if you cannot, let's not worry about it.
Like I'm not able to move it.
Interesting. Okay.
Sorry for that.
No worries. No worries.
Yeah. Okay. Right above the title. Okay, so one idea to tackle this problem is like to better understand like what is going on in neural networks in these black box architectures, and what you can do is like to break them into simpler building blocks that you then can study. And I'm particularly interested in studying neural networks or simpler building blocks through the lens of dynamical systems. So you can view neural networks as a dynamical system, and if you do that, then you can actually port a lot of interesting theory from the dynamical systems community over to machine learning, to deep learning, and try to understand better what is going on. So kind of this is slightly different than just applying machine learning to a dynamical system problem. And kind of what are the connections at a high level, for instance, and I will talk a bit more about this later, is like there's like a rich connection between different network architectures and numerical methods. And you can build a connection between different training schemes and stability and control theory. So I will show a bit in this talk how some of these ideas help us to better understand what is going on. Okay, let me talk a bit about ODE nets. I keep this really, really brief, but just so that we are all on the same page. I assume you're all familiar with an ODE initial value problem, but in many situations, we don't know the right-hand side, so we can't explicitly formulate what f is. So the best we can do is collect some observational data. And then the idea of an ODE net is to approximate the right-hand side using a neural network given some data. And you can here kind of plug in your favorite neural networks. It can be a fully connected neural network or some convolutional neural network. So depending on the problem, whatever works best. Okay, so what do we get from this formulation? I mean, first of all, if I formulate it in continuous time, I cannot train it because at the end, if I want to train it, I need some discrete form so that I can build a computational graph. But like from a theoretical point of view, I can kind of study some of the behaviors of such a neural network, which has been done recently very successfully. And kind of this view is actually not new. If you go back in time and look to early work by Rosenblatt, he formulated already neural networks in continuous time. And then Rico Martinez has kind of proposed this formulation, but it got really popularized just recently by Shen, who got like the Best NeurIPS paper award for his paper on neural ODEs. Okay, so basically in order to train it, we need to discretize the model. And well, we can just look into our textbooks on numerical analysis and pick some numerical integration scheme, right? So the simplest scheme we can pick would be an Euler discretization. And you see now immediately the resemblance to a ResNet. But we can also choose some more interesting integration schemes like Arca4 Classic. And that would kind of, if you look to the connection, this would looks very similar to a DenseNet. And kind of the difference is like that in a ResNet, we have to evaluate like our neural network block only once, where in an Arca4 scheme, we would need like 4 evaluations. So it's more computationally expensive to train a network with the scheme. But I'll show you in a second that it, in some situation, has some advantages. Before I do that, I just want to make you aware that kind of this view is at some point, like we have to be a bit cautious here, right? Because numerical integration works in a different direction than learning the dynamics using a neural network. So numerical integration, typically we start with a known f, and then we discretize it, and then we generate some data. What I'm proposing here with neural ODEs is we are given some data, and then we minimize some loss function, let's say like the mean squared error, and we hope we get a good approximation, or we learn a model R, which is a good approximation for this unknown f. And that is what we see typically, or quite often not the case, in particular not if you use the forward Euler integration. Okay, here's a question, I guess. You can also train it with adjoint sensitivity methods like okay, yeah, that's it's a good hint from Robert. I haven't looked into that but yeah, very interesting.
So Robert commented that you can also train it with the adjoint sensitivity methods, like with CVODEs done here at LLNL. In that case, you are still doing everything in the continuous method, but you are only using the backprop for the objective error. at each integration point. I just read it for the folks who will watch this YouTube video later, who will not have access to the chat.
To kind of expand on that, you can actually specify just a standard adjoint sensitivity optimization, which is done with some software packages here. But in that case, what you need to do is you have some goal function, which is like the L2 norm of the error between like what you're outputting and what the training data is. And then your all you need is the back propagation for your local neural network inside the adjoint sensitivity to properly differentiate the goal of the L2 error at that integration point. So you end up not needing to take a bunch of time steps. You can use adaptive time stepping for the whole thing.
I see. Okay, that's interesting. So I might ask you a follow-up question, but let me go with a slide because
sure.
What we saw is like, okay, what surprised us a little bit is originally like this, like what quite often you read now in the literature is that a ResNet is actually just a forward Euler discretization. But what we see in practice is that kind of this forward Euler discretization of a network behaves different than what we would expect if it were an actual forward Euler discretization. So what do I mean by that? So let's look like at a very simple dynamical system, just a nonlinear pendulum. And so we generate some ground truth data, which is shown here in by these blue squares. Okay, so if you use the forward Euler discretization and don't make the time step too small, then we know a forward Euler will diverge if we use a numerical integrator. But what happens if we use the neural network discretized with forward Euler? It basically fits the data perfectly fine. Similar with ARCA4. Okay, so it seems like the forward Euler discretization is learning through the integration scheme and provides us with good, accurate point prediction. But if like the function we have learned were meaningful, that means like during inference time, we should be able to change like the delta t or delta t and kind of be able to go smaller time steps. And if we do this, we see like this conversion plot on the right-hand side. And if you look to the red line here, that's for the Euler ODE net, we see like if we slightly change delta t during inference time, then the error increases. And that is not consistent with theory from numerical analysis, where we would expect like for forward Euler that the error is decreasing if we decrease delta t. But if we train a neural network with ARCA4, then we see like that we have the right behavior, that if we decrease delta t, the error during inference time is also decreased. So it kind of matters how we discretize a neural network if we want, for instance, use this model to interpolate points between two points we have observed. Using just forward Euler did not work. We tried adaptive time stepping methods, and on this problem he has different schemes, and they didn't do too well. But it's a bit different, a bit challenging to do this conversion analysis with those models. But the point is we have to be very careful how we train a neural network if we want to use it for scientific applications, particularly if you want to later interpolate data or extrapolate data, and not just simply predict a single target given a single input. And if you're more interested about this, I don't want to dwell too much on this topic, but we have recently posted a paper on learning continuous models for continuous physics, which exactly discusses this issue. Okay, good. So this was like just a brief overview of what I mean by an ODE net and how I think about like a continuous time formulation of a neural network. And obviously there's a lot of exciting work going on. So now I take this view and apply it to recurrent neural networks. But if you have any questions, I can pause for a second.
Do you have any challenge, training the ODE nets?
So it depends what your task is. So if I just want to get a good point prediction, they're very easy to train, right? These are very simple networks. I mean, obviously it depends a bit on the problem you're looking at, but they're easy to train. Even, I mean, we just use backprop. The challenge is like to learn a meaningful approximation of the right-hand side of a differential equation, right? So by meaningful, I mean like that I'm able during inference time to interpolate points in between data that I have observed, that I can make delta t or my time step smaller or larger. So that is like indeed a bit tricky. You have to be careful, but using higher order integrator schemes help us to learn a meaningful approximation for the continuous dynamics.
How about the large system of ODEs? Like you have many variables.
Yeah, we have it works as well. We have applied it to some fluid flows. Basically, you can plug in like this framework or combine it with an autoencoder or an autoencoder architecture, where you first learn an embedding and then basically learn the dynamics in the middle to evolve the system. So of course, like if the problem gets larger, I mean, it is challenging, but we get good results. Yeah, so it's pretty promising.
Very good. Thank you, Ben.
Okay, perfect. Okay, let me switch to recurrent neural networks. They have somewhat a bad reputation for some reason. Mainly, I think there was like up to probably 5-6 years, it was somewhat challenging to train recurrent neural networks because they have some stability issues. But I will show like that kind of this problem can be solved. And now I think modern recurrent neural network architectures achieve state-of-the-art performance and quite often outperform LSTMs, and in some cases even transformers if you have very basically very long sequences you deal with, because in those situations a transformer is just not feasible. So just as a reminder, what is a recurrent unit? It's like a very simple architecture actually. So here's a difference to a standard feed-forward neural network is that we basically have some feedback connection or some form of a memory by learning a hidden state H. And what we do at every update step or iteration in our model, we update H by using this update function on the right-hand side, where we basically have a W, which is a hidden-to-hidden matrix. And we have, in addition, like an input-to-hidden matrix, which takes like the current input at time t. And then you have a bias term, and we just wrap around some nonlinearity. Typically, we use a tan-H function here, but there are some other versions of nonlinear functions that you can use as well, depending on the problem. And you can expand this, of course. I mean, instead of just having an input-to-hidden matrix, you can put here some encoder, which is like nonlinear. But that is a simple basic recurrent unit, which I don't know, I think probably it's like got popularized in the late 80s. So it's around for a while. Okay, but the problem is like, just assume we have like a linear discrete time dynamical systems, and you're well aware, right? I mean, that we can have like an issue of that the dynamics either vanish or explode, depending on the eigenvalues of this linear map A. And in an or kind of, at least for learning, the problem is like if the dynamics quickly converge, then we have during training, then this leads to a vanishing gradient problem. On the other hand side, if the dynamics diverge, then this leads to an exploding gradient problem during training. So in some sense, during training, we would like a model which is on the edge of chaos. That means like for a linear model, we won't have eigenvalues on the unit circle. Okay, but our recurrent neural network is not linear, it's nonlinear. So kind of the analysis is a bit more challenging than just computing or looking at the eigenvalues of this model. I switch over this model. So doing this analysis in discrete time can become really challenging, in particular if you consider in addition some gates or some more modern variants. And it's actually much nicer if you consider a continuous time formulation of a recurrent neural network, as I do here in equation 4. So a simple idea here is like if you formulate it in continuous time and you want to check whether your model is stable or not, or in which regime it is, you can compute the Jacobian, and then you get some local analysis for stability by checking the eigenvalues of the Jacobian. So one idea here, which has been proposed, like called the antisymmetric RNN, would be then from this analysis to consider an antisymmetric matrix for W, which basically leads to a matrix that has only eigenvalues that are imaginary. So you can show like this model neither has diverging nor converging dynamics, so it is on the edge of chaos, and it does not have like these issues of exploding or vanishing gradients. In practice, it turns out this is a little bit too restrictive, and also that provides you only with a local analysis. So what we try to do in our Lipschitz recurrent neural networks is to come up with some global analysis. And to do that, we had to slightly change the architecture. Basically, we introduce this additional linear term in front of the nonlinear term. So we have like now a unit which is designed by like a linear component plus a Lipschitz nonlinearity. And again, we just assume here that this nonlinearity is like an M Lipschitz function. And if we do this, then we can use some nice results from control theory to study like basically the properties and show that this particular recurrent unit is globally exponential stable under some mild condition on the hidden-to-hidden matrix A and W. In particular, what we require is that the eigenvalues of the symmetric part of A or of asim are strictly negative, and that W is non-singular. And then we also need to ensure that the smallest singular value of asymmetric is larger than the largest singular value of W. Okay, so if we can satisfy these conditions, then our recurrent unit is globally exponential stable. So knowing this, that helps us now to define like some scheme to design A and W in a way so that we basically can satisfy these conditions. And the idea is basically by using a symmetric skew decomposition for constructing these hidden matrices. So we design like some matrix S or some weight matrix S as a convex combination of a symmetric matrix and an antisymmetric matrix. And in addition, we have like this term gamma I, which allows us to shift the eigenvalues to the left. And well, it's not difficult to show that we can basically also basically the eigenvalues of this matrix S lie in the following interval. So what I'm saying here is we can ensure by tuning beta and gamma so that the eigenvalues are strictly negative. And we can also ensure that, for instance, like the smallest eigenvalue of A is smaller than the largest eigenvalue of W. And I just want to basically illustrate this quickly. So here is like an arbitrary weight hidden-to-hidden matrix. We set like beta 2.5 and gamma 0. So you see like this matrix has eigenvalues that are like here positive eigenvalues. So this matrix would like lead to exploding gradients. But now if we crank up beta a little bit, we squish like the eigenvalues towards the imaginary axis. And then I can add like a little bit of gamma here and shift the eigenvalues so that all of the eigenvalues are negative. So in this case, like the dynamics cannot diverge. And like design and tune the ellipses are has a nice behavior during training time. Okay, so here's putting everything together. Basically, we just replace like A by our skew symmetric decomposition and W as well. So the disadvantage is that you have like two additional tuning parameters, or actually 4 additional tuning parameters. But in practice, we see like these choosing like these tuning parameters is it's not very difficult. So for all of our experiments, we use basically the same tuning parameters. So it works pretty well out of the box for new problems. Okay, and then again, this was like a continuous time formulation, which helped us to analyze what is going on, motivate a new architecture, bake in some structure into our neural network. And then in order to train it, we just pick some numerical scheme for discretization. And in our experiments, we choose Euler and AK4 classic. So let me show you some results that it actually works. So I'm starting with a simple time series classification problem. Basically, you have sequences or time series from some belong to class R and some belong to class B, and then the task is to basically classify a new time series during inference time. And so here, why not using just standard feed-forward neural network? I mean, the big advantage is with the recurrent neural networks, you can deal with time series which have different or varying lengths. So that would be difficult to do with a feed-forward neural network. Okay, so here are some results to show that what we're doing works fine. This is like on the pixel by pixel MNIST benchmark problem. And there are 2 variations. We kind of use the ordered sequence. So basically what you probably all know MNIST, right? So you have like a little thumbnail, you flatten it, and then you treat it like as a sequence. So basically at every time t, you feed in a pixel at the t's location of your vector. And then the other option is that you scramble all the pixels and work with a permuted sequence. So that really requires the model to have some memory in order to do the right classification at the end. And here you see like LSTMs do not do very good on this task, particularly not on the permuted task. They get just 92% or 92.7% accuracy. More modern LSTMs, like the momentum LSTM, is doing a little bit better. And we get like with our, and basically this has 250K parameters. And with about 34K parameters, we get 96.3% Lipschitz RNN. So indeed, this model is easy to train, and it features or has some good expressivity and learns like to memorize important points from the past. Okay. Also, what was of interest to us is to understand whether such a model is more robust. Here by robustness, I mean like more robust to some small input perturbations. And here's like a simple plot where we basically evaluate during inference times the test accuracy as a function of amount of noise that we add. I think here we just added white noise. And you can see that Lipschitz RNN out of the box is a bit more robust than, for instance, the antisymmetric RNN or other recently proposed RNN architectures, such as the exponential RNN or coupled or solitary RNN. And I think like one of the reasons is like really that you bake in some stability here, so you know your model is stable, and that way it is more robust to small input perturbation. But kind of this motivated us then to do a bit more work into this direction, and led to the formulation of noisy RNNs. And basically the idea is like generalizing the idea, why just considering an ODE, we can also consider a stochastic differential equation model. For instance, we can consider the following Ito SDE model here. And kind of where F is some drift term, and sigma here is diffusion term. Sorry, so it's a bit confusing. So sigma here is not a nonlinearity, but it's like referring to a diffusion coefficient. And then what we do is like we basically choose for F our Lipschitz recurrent unit. And for sigma, we basically choose some noise model, and we consider here additive plus multiplicative noise. So we have like, in addition, like 2 new tuning parameters to modify like the noise levels. And if you do this, basically what we do is here is we start with an SDE, but it can be viewed like as some form of noise injection that we do, and that helps us to improve robustness. What I want to stress here is we inject noise in the latent space, not in the input space, right? So that's slightly different to adversarial training, where you add noise in input space. And kind of that's a simple noise model we consider here. So depending on your particular problem, you might know what kind of noise you deal with, so you can switch out this noise model. And here are some results which I think are interesting. You can really see that for white noise perturbation and salt and pepper noise perturbation, the noisy RNN is substantially more robust compared to the Lipschitz RNN and also to these other RNNs that I showed before. But it does not lose much performance on clean data in case if you don't see any perturbations. And kind of the training time is roughly the same. So in practice, right, I mean, the question is which model would you prefer, particularly if you have like a mission critical application or some medical application, right? It's a more robust one or it's a less robust one. So I would prefer like a more robust network, which I know is less sensitive to small input perturbation during inference time. And like using like this SDE framework, so I'm not dwelling too much on theory here, but if you look to the paper, you can like study this neural network through the lens of stochastic differential equation, and for instance, make statements about implicit regularization, again, about stability. So kind of this view, viewing like these neural networks through the lens of dynamical systems opens up just a nice toolbox to do some interesting analysis and understand some nice properties. Here's another example where we look like at electrocardiograms. And again, it's like a classification problem. I think we use like here 500 sequences of length 140 for training, and then 4,000 sequences for testing. And we want to classify whether the heartbeat of a patient has some severe heart failure or whether it's normal. And kind of our current neural network is doing a pretty good job to provide an accurate prediction. So you see like you get 97.7% accuracy here. And again, like the noisy RNN provides you with more robust predictions, even if you have some perturbations in the inputs. Okay, so here's some theory about regularization, but I skim over this. So if you're interested, just have a look to the paper, or you can drop me an email. So I want to use like the last 5 to 10 minutes for talking about LEMS. It's our latest work, which just appeared at ICLR in spring. So what basically, there are like these two challenges in sequence modeling using neural networks is on the one hand side, you want a model that is very expressive, but you want on the other hand side also a model that is able to learn long-term dependencies. So LSTMs are known to be very expressive, so that's why they're very popular, but they are not really good at learning like long-term dependencies, which I showed like before on this MNEST, pixel-to-pixel MNEST, where you have a very long sequence. So they underperform there. But then like these other models here, particularly like these continuous time models, are not as expressive, but they're really good at modeling long-term dependencies. I think particularly Unicorn and Corn, and they showed example that they can deal with sequences up to, I think, a length of 18,000, which is extremely long. So that's very impressive. So, well, what kind of basically led us to the question, how can we design a new model which is both expressive but also be able to learn some long-term dependencies? And kind of so we asked like, what is the problem in general with the current models that we consider? And one of the issues is that like these ODE-based RNNs assume a fixed time scale, and that's a pretty strong assumption for many problems that we deal with. So the idea is kind of to formulate like a model which allows to model many time scales. So at the simplest case, right, we could just start with a simple, or consider a simple system of 2-scale ODEs here, where you have like tau y and tau z that are kind of able to model 2 time scales. But 2 time scales is also very restrictive. It's nice to have like the slow and fast variables here, but we can generalize this idea so that we can tackle more complicated problems. And if we do this, we get like this nice multiscale version that's provided by this following set of ODEs here. So here sigma hat is now a sigmoid function. So basically the values you get here get squished between 0 and 1. So this first block here can be seen at some point as a gate, or kind of modeling these different time scales, which we then multiply with the second block, where here sigma is a tanh function. And basically that is the fast varying, or models the fast varying variables, and then we have this second block here, which models the slow varying scales. So this is a coupled system, and again, we can discretize the system using some implicit explicit time stepping scheme, which leads to these following equations here. So if you look at it, it looks like a little bit like an LSTM, and under certain conditions there are similarities. We discuss this in this paper. And what is nice is, like, if we study this discretization here, we can show that this particular model is mitigating exploding and vanishing gradients. And we can also show that this model is a universal approximation of general dynamical systems, and also like a universal approximation of multi-scale dynamical systems. So it's a pretty powerful formulation, again, motivated by dynamical system theory. And if I show you some results here, that is like on the Google 12 task, which relates, I think that's like pose estimation. You can see that the LEM is outperforming previous models quite a bit. So that's like on expressivity task, but it's not that much better than a gated recurrent unit, but quite a bit better than LSTMs. And indeed, what we want to show here, it's better than like these exponential RNNs or co-RNN, which are known to be not that expressive. And that's similar like to like some natural language processing, where we try to predict some characters in a sentence, and we see like we can greatly improve the performance using LEMs. And I think the results are more impressive even on long-term dependency tasks again, at least compared to LSTMs. So here's like a task like where we try to do heart rate prediction again, but it's like with a longer sequence of 4,000. So LSTM really do not learn anything meaningful. Exponential RNN is learning something, but it's not really impressive. And then LEM is doing really good on this task. And this is like this eigenworm problem, which considers a very, very long sequence. It's a genomics data set. And we get like some really good performance compared to other RNNs. So in summary, LEM provides like a really interesting alternative to LSTMs out of the box. We have also like a high performance implementation written in CUDA, so you can just plug it into basically, or just use it as a plug-in replacement for LSTMs. And it's nice to see it has now recently been used, or started to be used by Microsoft for some of their problems. So it gets some traction. It turns out to be actually useful in a broader range of applications. Here's a quick example, like for a multiscale system, just to basically as a sanity check. I mean, do we actually learn some interesting multiscale structure? And here we can see, yes, so there's an advantage of modeling like these different timescales using LEM compared to other RNN and LSTM models. Sorry, what I want to show here is, basically what we show here as well is just ablation study. And the second plot is like, if we use LEM but we switch off the multiscale structure, then it does not learn really anything meaningful, but if we allow the LAM to learn multiscale structure, then we get really good performance. Okay, perfect. I switch over to my summary so that there is like a little bit of time for question at the end. So mainly what I wanted to present here is like motivate is like this idea of ODE networks or viewing neural networks as dynamical systems is very useful for many physical or financial applications where differential equations are natural. ODE nets are good for modeling irregular sample data. That can be done with standard discrete time neural networks. And kind of, I think, exploiting this connection between dynamic assessment and deep learning allows us to develop more interesting models that we can better understand and that also are more robust at the end. I showed like that kind of using like a stochastic differential equation can be seen as some stochastic learning strategy, and like it's a very simple trick to improve robustness, and that's like really important in some applications where we know we deal with noisy data during inference time. Okay, I stop here, and
thank you so much for the wonderful talk, Ben. Oh, very nice, very nice.
Thank you.
Okay, is there any question from audience? There's no question in the chat other than Robert's the comments. Well, let's while you guys think about it. Ben, can you go back to the slide where you talk about Lipschitz recurrent units?
Sure.
It seems to be pretty interesting. And by looking at the, you know, the formulations, structure.
Okay, I think here, for instance, this one.
Yeah, for instance, that one. And can it be viewed as, okay, so here you're designing the right-hand side with some linear term and
yes,
some non-linear term, which is represented by neural net.
Yeah.
Can it be viewed as basically it is a DMD, is, you know, the DMD kind of modeling is taking upon with the first terms, like the linear terms, and then second term is kind of representing the error of the DMD and quantified by the neural net.
Sure. I mean, you can probably have many
interpretations,
viewpoints here, right? So to be fair, originally my motivation for this model, so there's like in the control community, there is like this class of Lipschitz systems, which have exactly this form, like a linear term plus a nonlinear term. And I think it is, this particular formulation allows you to do some global analysis, which you can't just do if you have just this nonlinear term. So that was the motivation here, considering this particular form to do this global stability analysis. You can think about in many ways about the linear term, while you have it there, and kind of from a perspective on like, yeah, you can say, okay, the linear term is modeling basically the linear component, and then you have like the residual, which is modeled by the nonlinear term. So that's different viewpoints you can take.
Sounds good. Okay. You know, a follow-on question on this topic. Probably next slide or previous slide, you show the conditions that the activation function needs to satisfy, like the Lipschitz continuity.
Yes.
And I guess not all the available activation functions satisfy that.
Yeah, that's true. Not all. I'm saying here, not all activations are M Lipschitz.
Right.
But in some sense, I mean, most of the times for recurrent neural networks, we use a TAN-H function, which satisfies this condition.
Agree.
It's not very popular, or you don't see many other activation functions in the mainstream literature. So there are like some more exotic one, like some modified ReLU function. It's used, I think, in the exponential RNN, but that typically doesn't work like with other architectures. So yeah.
My
Sure.
follow-up question is: Have you tried with those activation functions which does not satisfy the Lipschitz continuity?
I see.
Does it still work? I mean, usually the theory and practice.
It's a gap. So okay, so one thing is like, of course, I mean, these are, I say, like conditions which needs to be satisfied. In practice, I mean, we look to the eigenvalues. So we do not. I mean, depending on how you tune it, you can actually kind of meet these conditions. But even if you don't meet the conditions, we show, like, we have some ablation studies where we plot like the eigenvalues of A and W over time. And it works surprisingly well if you're slightly off. But we show also ablation studies if you basically, if you choose like beta here, like 0.5, you get really poor performance. So we have basically a plot which shows you like that you want to be somewhat in this regime here in the middle, or even better here on the right-hand side, right? But even if you have a situation where you do not satisfy the conditions exactly, you still learn something. But if you're too far away from satisfying the conditions, then suddenly you don't learn anything anymore. So there's a little bit of gap of what you see in practice and what you have in theory. I also want to mention, right, the theory holds like for the continuous time formulation, but we do the additional discretization step, right? So it depends also a little bit how large you choose like your delta t for discretization.
I see.
Yeah. So sometimes we haven't done this. I mean, we could do the analysis in discrete time as well, but it was like more like conveying a point, like having this idea of viewing a model as a dynamical systems, and then doing this analysis and motivating, like basically what was the motivation is like coming up with this symmetric skew scheme, which turned out to work very well.
I see. All right. I shouldn't ask too many questions. Okay, so there are questions from the chat room by Andrew. He asked, for the ECG example, how long did it take to train the neural network?
So I don't know. So there were like basically two ones. So there's the I think like the smaller one, which was used pretty short sequences. I think the training time there was very fast. I think maybe half an hour or so. But for the second example, we considered in LAMS for the long sequence, that is of the order of days. That's like really challenging to train. Because like as long as the sequence gets, it's painfully slow to train recurrent neural networks. The unicorn model, so, is very fast. So if you look for something extremely fast for these type of problems, I would recommend to have a look at the unicorn paper.
Okay. All right. Next question is by Rob. Okay, so when you look at the eigenvalues of the matrices being generated by your neural network, are they close to what you would expect from a nonlinear system analysis standpoint? In other words, do you end up generating stiff differential equations for stiff problems?
Oh, I see the second question. Yeah, that's a good question. So in some sense, like these mainly what we've done with RNNs, where I look to the eigenvalues, I haven't looked to too many dynamical system problems actually. So here again, the idea was like using ideas from dynamical systems to develop new neural network architectures. What I talked about before in the ODE context, that's a good question. I haven't looked to the eigenvalues there. So basically there we just did this conversion analysis So we considered a lot of different dynamical systems there. And the question was just basically, does the model pass the conversion test or not? I haven't looked to the eigenvalues of neural ODE. So that's a good question, but sadly, I can't give a good answer to it, but something I should probably investigate.
But you do compare the solution itself, not the eigenvalues, you know.
Say again?
You do compare the solution itself, like the solutions from the underlying
Yeah.
ODE and your neural ODE, recurrent ODE.
Yeah. That we do. I just don't know. Like again, I think we have considered stiff systems there. I think the nonlinear pendulum in the XY was XY coordinates. That's very stiff. And what we see in general, it's harder to train these problems. But I'm not exactly sure how the eigenvalues look like.
Well, I think if you go back to the beginning where you're showing some of your plots comparing the numerical Eulers to what the network is producing, like here's a case where Euler is going crazy due to stiffness. And the neural network is doing just fine. So what I suspect you will find is that you don't have the stiffness that you would expect to have in the integrator, just looking at this plot and looking at the plots there on the right. And I think it'd be really interesting because I think what your neural network is actually doing, if you plug in a fixed time step, it's actually solving both the numerical, it's solving the right-hand side and coming up with like a specialized integrator for that problem.
So that's my point, right? It's learning through the integrator right? So it comes up with something in some sense, right? If you use forward, sometimes basically if you use forward Euler, you have no inductive bias during the training process. With ARC4, if you use like this more complicated scheme, so you give the room, you introduce some inductive bias, and you give like the model less room to learn something outside of the scheme.
So I would be super interested if you say try to teach one of these neural networks on continuity. So like take a problem where you have the analytical solution, right? And then just very time step wildly and plug in the analytical solution and see if you can actually come up with and have the time step be one of the parameters for your sequence, and then see if you can develop a network that can integrate this thing in a stable manner no matter what the time step is. Because I mean, as from a neural networks, from like a sequence training point of view, that's not super useful, but from a numerical methods point of view, that's extremely interesting.
Maybe we should touch base offline and talk a bit about those ideas. I think that would be great.
Okay, cool.
Rob, I have a question for you. How wild time step variation are you thinking here?
As wild as you want.
Okay. All right.
Basically just enough to kind of teach the model continuity. And sometimes I would like deliberately plug in like a time step of 0, just so it like handles the limit condition. But you kind of want to teach the model how to converge, right? Because I mean, the big problem I'm seeing with the when you do convergence on the neural network, you train at different time steps, it doesn't seem to be converging. But I think you can train a neural network how to converge by varying the time step. Because I mean, that's the constraint that we put on numerical systems, and we know that they can do it. So it'd be really interesting to see if the neural network could find this.
All right, sounds good. Is there any other questions? We passed the 6 minutes, actually, the promised time. If not, let's thank our speaker, Ben, for the wonderful talk. I personally enjoyed a lot, and I learned a lot from it, from the talk. And yeah, I mean, it's a wonderful job, and I'm sure there will be fruitful future collaboration between us and you.
Thank you so much for the invitation again. It was great.
Awesome. All right, let me stop the recording.